All right, you guys, you've made it almost to the end of stoichiometry, so that's exciting. What we're going to be doing in this lesson is looking at what a limiting reactant is. This is also referred to as a limiting reagent, so the reactants can also be called reagents, and you'll see that in the video you watched prior to this. The reason why we have to be paying attention to what is limiting and what is in excess is that in real chemistry, it is really, really hard to get the exact amounts of each reactant that you need. So typically what a chemist will do is they'll take a look at which chemical that they're working with that is the most expensive, and that usually is their limiting reactant, and they'll throw in excess of the cheaper just to make sure that all of the expensive chemical is consumed. And they usually determine what amount of expensive chemical they need based on how much product they're looking to actually create. So a limiting reactant in chemistry is the reactant in a chemical reaction that limits the amount of product that can actually be formed. In the Professor Dave video that you watched prior to this, he was talking about the creation of bologna sandwiches, and in his example, the bread was the limiting reactant. And even though you had more bread available to make sandwiches, it was what was limiting the actual equation that he was deriving. All right, so what we're going to be looking at is one method for solving these problems. Now, I will be honest with you, limiting reactants do require a bit more brain power and a bit more patience. There are several ways that you can actually solve these problems, but I'm going to just show you one way that I like to use. Just it kind of like helps me with questions down the road. All right, so in addition to looking at the limiting reagent, we're also going to look at what is excess. So that again is usually the cheaper chemical that we are throwing just copious amounts of into the reaction just to make sure that the reaction goes to completion. In these problems, you'll have to identify a wide variety of things. First and foremost, you'll have to determine what reactant is limiting. Once you determine that, then you have to determine that the other reactant is the excess. You usually have to then tell how much of that excess reactant is left over. And again, I'll show you how to do that in a few steps here. Another thing that you have to do is predict how much product should be produced. So this is usually how many grams of product will be produced. The example that we're going through in this video is going to walk us through all of those types of questions and then just how I would solve them. Again, like anything in chemistry, especially with stoichiometry, the more you actually see these and practice these problems, the easier this skill becomes. Obviously, at the end of the year here, we're running out of time, and with our distance learning plan and the shortened amount of time that we have left, so you'll just get a kind of a good taste of this concept. All right, so the example we're using is one that you guys would have seen in the precipitation lab where you were mixing clear solutions, and silver nitrate and calcium chloride, when you mix those two together, formed a milky white precipitate, which was the silver chloride, and then calcium chloride was still floating around in aqueous solution. So the first thing that we need to look at is if we're starting off with 5 grams of silver nitrate and 2.5 grams of calcium chloride, what would be the limiting reactant? Again, as Professor Dave said, you can't just look at the thing, you can't just look at the grams here and say, oh, because there's only 2.5 grams of calcium chloride, then that's going to be the limiting reactant. You also can't look at the fact that in silver nitrate, it's a 2-to-1 ratio, 2 silver nitrate moles for every 1 mole of calcium chloride. And you can't say, oh, well, there's 5 grams of silver nitrate there, and that's twice as much calcium chloride, so this looks like it would be perfect. You really do need to take the step of converting from grams to moles. What I'm going to do here is a little bit different than what Professor Dave did. I am actually going to take the grams of what I think might be the limiting reactant just based on the molar mass and based on the fact that so much more of it is required. And I'm going to find out how much of the other reactant is required. So looking at my problem here, I'm going to take the 5 grams of silver nitrate, and I'm actually going to start with that. So 5.00 grams of AgNO3. Again, guys, this is just a hunch. I actually haven't worked this problem out prior to making this video, and I just am going to start with one. And if I'm wrong, I still know my answer, and I'll explain that to you in just a second. So I'm going to need to calculate out the molar mass of silver nitrate. And again, that's where stoichiometry tends to take a lot of time. So the molar mass of silver nitrate, after I've worked it out, is 169.91 grams per mole. For the purpose of this video, I am going to continue to write out all of the labels, again, just to show you that it is unit cancellation, okay? What I want to do is I want to figure out how many grams of calcium chloride would be required if all 5 grams of my silver nitrate would be consumed. And I'm looking to see, do I have that? You know, do I have enough calcium chloride? All right, my next step here, I can't go from grams to grams without using a mole ratio. So I'm going to put down 2 moles of silver nitrate. And this is coming again from my balanced equation. Is required for every 1 mole of calcium chloride. And if the problem had given me moles, I could actually stop here and just say, you know, do I have enough moles of calcium chloride? But the problem gave me grams, which is the most common thing that these problems will do. So I'm going to have to convert all the way to grams of CaCl2, which is what you spent the last part of your last assessment doing. So hopefully this is a little bit more familiar to you. Again, I have to calculate the molar mass of this compound. So 1 mole of CaCl2 has a molar mass of 110.98 grams. All right, and again, like I said, I hadn't calculated this out before, so I'm going to do that right now. So 5 divided by 169.91 divided by 2 times 110.98 gives me an answer of 1.63 grams of CaCl2. All right, so what is that information telling us? It's telling us that if we want to use up all 5 grams of silver nitrate, then we would need 1.63 grams of CaCl2, all right? We have that, right? So we have 2.5 grams of CaCl2, which means that silver nitrate will be our limiting reactant. Once the 5 grams of silver nitrate is used up, the reaction will stop. We have extra calcium chloride that will be left over, and that's going to actually help us answer our next question. So the limiting reactant here is AgNO3. This is going to be the reactant that we are going to use to solve the product problem in a little bit. So the next question is, what is the ER, which means the excess reactant, and how much will remain at the end of the reaction? Well, again, we determined just a bit ago that calcium chloride was the excess reactant. And the neat thing about what we just did is that we know how much was used. All right, we know that if 5 grams is used, then it's going to be 1.63 grams of CaCl2 will be required. So all we're going to do now is take how much we started with, which is 2.5 grams of CaCl2, and we're going to subtract out that 1.63 grams to get our actual answer. And that's 0.87 grams of CaCl2 will be left over. Now this is assuming a perfect situation where everything has gone perfectly and the ratios were beautiful and there were no side reactions or anything, but we could expect to see 0.87 grams of CaCl2 will remain. Now, if I had gotten my guess wrong, like if CaCl2 was the limiting reactant instead of silver nitrate, what we would have seen here when we did the problem is that we would have needed more CaCl2 than we actually had. And so then we would have determined that CaCl2 was the limiting reactant. We would have to go back then and start off with 2.5 grams of CaCl2, convert over to grams of silver nitrate, and then subtract 5 minus whatever that answer was. So sometimes our guess is great and we're right and it's wonderful. Sometimes we're wrong, but in our mistake, in our misguessing, we actually get the answer that we're looking for, and then we just have to do a few more steps of math. Again, be patient with these problems, you guys. It just requires, it's a lot of grams to grams conversions, okay? All right, this is the next thing that you'll be asked. How many grams of each product will be produced? Now, this is based, you guys, on the limiting reactant, so it's really important that you figure that out. All right, we know that silver nitrate is our limiting reactant, so I'm actually going to save myself a little bit of a step here, and I am going to cut out the first 3 steps of our problem from above. And the reason I'm doing that is I know that all 5 grams of silver nitrate will be consumed, okay? And I already know the molar mass of silver nitrate. I already know the 2 moles of silver nitrate. The only thing I'm going to change here is what I'm converting to. So in our problem, we're actually looking to find, apologize for the jumping around here, we're actually looking to find how many grams of AgCl we're going to be producing. And then also how many grams of calcium nitrate. And so we're going to just use the limiting reactant to determine that. So I will start off by saying we had 2 moles of AgCl. Again, I'm just using mole ratios here, and I'm going grams to grams. So my last step in this process is going to be converting from moles of AgCl now to grams of AgCl. So 1 mole of AgCl has a molar mass of 143.35 grams. And I'm going to come back and set that up here in just a moment. But before I do that, I want to just do my last one, which is the calcium nitrate. So again, I'm going to paste in the first part. Instead of writing it all over again, I'm going to change this to calcium nitrate. Again, that was 1 mole of CaNO3 2. And then in this last step, I have to use the mole mass. So 1 mole of CaNO3 has a mass of 164.10 grams. All right, and we'll go through and calculate that out. So 5 divided by 169.91. Our mole ratio is a 1-to-1, so I won't bother with anything there, times 143.35, and I get a mass of 4.22 grams. I'm rounding a little bit there, of AgCl. And then last but not least down here, so 5 divided by 169.91 divided by 2 times 164.10 is 2.41 grams of CaNO3 And those should be my answers. Now, something that's really kind of nice about this, the law of conservation of mass basically helps us out here, and that is the mass that I'm starting with for my limiting reactant and the mass that I'm using of my excess reactant. All of that should equal the total mass of the products that are produced. And again, this is in a perfect world, perfect scenario. Chemistry doesn't always work that way. So if I add together my products, so my 4.22 plus my 2.41, I'm getting 6.63. And when I go back and look at how much I actually used of silver nitrate, I used 5 grams, and I would have used the 1.63 grams, then I get 6.63 grams of reactant. So if you've done this correctly, you will be able to identify the limiting reactant, the excess reactant, how much of that is used, and then how much would remain. You'll be able to identify how many grams of each product. And again, at the end, the left side of the equation masses should equal the right side of the equation masses, which you start with, you have to end with. So that's limiting reactant stoichiometry, just doing grams to grams. Now, chemistry gets more confusing than this. There's a lot more layers added. We add in, equations and reactions where we've got more than just 2 reactants. You add in different conditions that can change the amounts that are being produced. You add in solutions, which adds in a whole other concept called molarity. you add in gas laws. There's all kinds of things that can complicate this process, but this is the beginning steps of stoichiometry with limiting reactants. One of the things that, I'll end here just in a second, but one of the things that my chemistry teacher was telling us in college, most of us were going pre-med, pre-vet, pre-something engineering. And he said a lot of times with chemistry concepts, you have to know the fundamentals in order to move on and to do the more complicated versions of things. He said, but something like with limiting reactants and stoichiometry, it requires dedication and patience. And he said, teaching us pre-med people that dedication and patience and resilience and being able to, make mistakes and work through those mistakes and keep on powering through, those were just really, really good life skills. And I don't want you guys to forget that. I don't want you guys to forget that sometimes what you're doing in school and in your own learning is more about being able to develop those critical thinking skills and that, that mindset of growth and perseverance, and that just when you come up against something hard isn't the time to quit, it's the time to kind of dig deeper within yourself. And limiting reactants gives you a great opportunity to practice your patience, practice your resilience. As always, guys, email me with questions. We can Zoom session, whatever you guys need to get through this last set of skills. There's just one more thing that I get to teach you, and that is percent yield. But I promise you that will be simple if you can understand this limiting reactant stuff. All right. Hopefully I'll talk to you guys soon.